Sometimes you can draw more than one valid Lewis structure for a molecule. So let's look at ozone. So ozone is 3 oxygen atoms. So those are going to be connected in a line. We're not going to do any ring structures or circular things in general chemistry. Wait, I'm getting ahead of myself. So don't try to make that into a triangle or anything. So I have 3 oxygens. They each have 6 valence electrons, so that's 18 valence electrons. I'm going to count the bonds first. 2, 4, 6, 8, 10, 12, 14, 16, 18, ran out. So 2 of the oxygens have octets, but this guy on the end does not. How do we fix it? The oxygen here that has 8 needs to share with the oxygen that has 6. Right? The person with more shares with the person who has less. That's how it's supposed to work. So now I've got an octet here, and here, and there. Octets for everybody. Yay! But there's another way that I could draw that structure. What if I put the double bond with the other oxygen? And we don't want to confuse this with just rotating the drawing. These oxygens are both oxygen atoms, but I think of them as being like identical twins, genetically identical, but they are 2 individual people, right? And if you give one a cookie and you don't give the other cookie, there could be trouble, depending on how old they are, I hope. So here, this oxygen got the double bond, and this one's like, why didn't I get the double bond? Oh, well, let's draw it that way, where you get the double bond and this one doesn't. Okay? That's not the same as just rotating. It might take a little thinking to get your mind around that one. So which one is right? Well, kind of both and kind of neither. So the molecule actually exists as an average of these 2. When we look at bond lengths, we observe that the bond length between both oxygens is the same. There isn't a short one and a long one. They're the same length. So they're between a single and double bond, both in length and in strength. So Lewis theory doesn't, handle that very well. So the best we can do in Lewis theory is to draw both of the structures and put a double-headed arrow between them. And these are called resonance structures. Resonance to me, also with the arrow, my brain always wanted to think that it was going back and forth, right? That's not what it's doing. Let's look at dogs. So there's a German Shepherd and, is that a Golden Retriever? I think so. So German Shepherd and Golden Retriever have a puppy together. It might look like this, right? Does this dog look like a German Shepherd 1 minute and a Golden Retriever the next minute? Go back and forth? No, that's ridiculous. It always looks like a combination of the 2 parents. This is what the real molecule looks like. It's a combination of these 2 structures that we can draw. Does that make sense? The problem is that electrons are localized in Lewis structures, so we have to say these electrons are, around this atom or around that atom, but in actuality, the electrons can be delocalized over several atoms or even the entire molecule. And that results in a lowering of the potential energy, which is called resonance stabilization. So this is our attempt at drawing the resonance hybrid structure These are the two resonance structures for ozone. Any questions? Let's do an example. Write the Lewis structure for NO2 minus ion, include resonance structures. So this is the nitrite ion. We have a nitrogen and two oxygens. What's probably going to go in the middle? The nitrogen. And the oxygens are terminal on the outside. And that's using that electronegative elements are usually on the outside. When there are more complicated formulas, a lot of times the question will tell you which is the central atom so that you don't have to fumble around. Okay, so made a skeleton, and now I need to count up valence electrons. How many valence electrons does nitrogen have? 5. I have 2 oxygens. They each have 6. And what do I do with the negative sign? Add 1 electron. So I believe that's 18. So now we put them around. I've got 2, 4, 6, 8, 10, 12, 14, 16, 18. This is working out just like ozone did because it's 3 atoms and the same number of electrons. So we don't get an octet here on the end, right? So the nitrogen needs to share one of its lone pairs with this oxygen on the end. And again, these oxygens, they are the same element, but they are distinct atoms, just like, twins are individuals. They have their own names and their own personalities and all of that. So how could we draw this differently? We could put a double bond with the other oxygen. What else is missing here? The charge. I need to put brackets. And I think the purpose of the brackets is just to separate the charge from all the dots so it doesn't get lost. So these are 2 resonance structures. And what we'll find in the worksheet we're doing today, in homework problems, in exam problems, most of the time when there's resonance in Chem 1A, it's moving a double or triple bond around, moving a multiple bond to another atom of the same element. So here we have 2 oxygens, there's 1 double bond. Who gets the double bond? Well, in actuality, it's a hybrid. They kind of all share it. But Lewis theory doesn't allow us to draw that. Any questions? Which structure is not a resonance structure of the ion shown here? You don't need to count electrons. They all have the right number of electrons. It's not A. So looking at resonance structures, we're looking at moving bonds around. We're not changing the skeleton. So do you see what's happening here in B? Nitrogen's in the middle, right? So we can't go between these 2 just by shifting electrons around. This would involve breaking bonds and remaking bonds. This is actually a completely different compound. So resonance structures are going to be different only in where the multiple bonds are. So this is not a resonance structure. So this is like the ones we were drawing, except with a triple bond. And this one, we're giving the triple bond to sulfur. And this is one of those somewhat unusual circumstances where it's not the same element. It's not two oxygens or two nitrogens. There's a sulfur and a nitrogen. So we can do the triple bond with one, the triple bond with the other. The other combination is to give a double bond to each of them. So there's actually 3 resonance structures for this one. Yes?
Are you going to give us a triple resonance?
So if you were drawing these, you would just put double-headed arrows between all of them. And yes, you could definitely get one that has 3 or 4 resonance structures. Well, how do we evaluate which of those is a better structure? Or are they all the same? So we use something called formal charge. This is a little bit like oxidation states in that it's made up. It's just something that we made up to help us keep track of things without thinking too hard. So it's a fictitious charge assigned to each atom. We're ignoring electronegativity. We're just looking at the Lewis structure. And, if you like mathematical equations, you can do that. I don't like that. So I'll show you in a minute a different way to do it. So formal charge rules 1 and 2 really could be lumped together if you say the sum of all the formal charges in a thing has to equal the charge on the thing. If it's an ion, it equals the charge. If it's a molecule, it has to be 0, which is the charge. Small or 0 formal charges are better. And when you cannot avoid a formal charge, if you have an ion, somebody has to have a formal charge. That's where the charge comes from. There are neutral molecules also where you can't draw one without having formal charges. So when you do have to have formal charges, you want to put the negative formal charge on the most electronegative atom, because that means that atom is kind of having extra electrons, and the electrons want to go over there because it's more attractive to them. And so that's going to be more stable. So let's look at this. So that's the way the book does it. If you like that, go right ahead. So I'm going to draw these structures out. So that's structure A. And this is structure B. Are these resonance structures? No, because the atoms are connected differently. But here there are 2 ways to connect the atoms and end up with octets. And so how do we decide which one is correct? Well, we're going to use the formal charges. So this is how I think about formal charges. So I think of hydrogen, carbon, and nitrogen. These 3 people came together and they formed a corporation. And their investment that they brought was their valence electrons. So hydrogen brought 1 valence electron, carbon brought 4, nitrogen brought 5 valence electrons. And they do business for a while, and then they're going to break up the corporation. And the way they're going to break it up is they're just going to cut all the bonds down the middle. It's like, well, that's just the simplest way, seems fair, we'll do that. So we're going to compare what the atoms brought and what they leave with. So we need to remember that each of these lines has an electron at each end. This is where half the bonds come in, but we don't have to think about it that way. So here's hydrogen. how many electrons did hydrogen bring? It brought 1. And how many does it leave with? It's going to take with it just this 1 electron. So oxygen, hydrogen breaks even on that. Doesn't gain or lose anything. Hydrogen always does that. Let's look at the carbon in the middle. How many valence electrons did carbon bring to the structure? 4. It's just group number on the periodic table. And how many electrons would carbon be leaving with? 1, 2, 3, 4. Okay, that's 0. This is kind of boring. Should have done the other one first. How many electrons does nitrogen bring? 5. And how many does it leave with? 5. So each of these atoms has a 0 formal charge. That's a good sign that that's probably the correct structure. Let's look over here at what happens when it's arranged differently. So we don't need to worry about hydrogen. He's always 0. So nitrogen brought 5 in group 5A. How many does it leave with? 4. So 5 minus 4 is positive 1. This has a formal charge of plus 1. Carbon brought 4 to the structure and it's leaving with 5. 4 minus 5 is negative 1. So this tells me that if we break this up in this way, nitrogen is going to be short an electron and carbon's going to end up with an extra electron when they break up. So here they're all zeros. If it's 0, we usually just don't write the 0 up there. Here we've got a plus 1 and a minus 1. These charges are higher than 0. So this is the correct one, the best one. Now, it doesn't mean that this compound doesn't exist, but this is the best Lewis structure for HCN. Any questions? So we're taking the molecule's Lewis structure and we're chopping all the bonds in half. So each atom that was participating in that bond gets 1 of those bonding electrons. And then we're going to look at, well, how many did this atom bring in and how many does it leave with? It's just a little bit of counting and some simple subtraction. Assign formal charges to each atom in the 3 resonance forms of N2O. N is central. So we would not expect you to draw that with N in the middle. So we tell you N is central. Which resonance structure is likely to contribute most to the correct structure? Well, what does that mean? So my ancestors came from Sweden. My husband's ancestors came from Japan. We have 6 children together. So our children are resonance hybrids, right? But as you may guess, somebody's genes contributed more to how they look than somebody else's, right? My children all have dark brown eyes and dark brown hair, right? I do not. So they look more like their father. He contributed more to the correct structure. So that's what we're looking at here. Which of one of these is going to contribute more? And we can look at formal charges to figure that out. So we're going to cut these guys up. Are you okay with not putting the dots on here? So, the end of the line here is an electron. So then for this nitrogen on the end, nitrogen always brings 5 electrons. And how many is it leaving with? Well, we'll count them. 2, 4, 5, 6. right? So that's -1. This one has a -1 formal charge. In the middle, there's another nitrogen. It brought 5. How many does it leave with? 4. So that's a +1. I'll write it down here because there's an A in the way. And then let's look at the oxygen. Oxygen brings 6, and how many would it leave with? 6. So that's going to be 0. That's not too hard. I think it's much easier than the book's way. Okay, so let's look at this one. Again, we're cutting these in half. And so this nitrogen always brings 5. How many does it leave with? 5. Okay, so that one's 0. And this one in the middle brought 5 and leaves with 4. 1, 2, 3, 4. So this is +1. And the oxygen on the end brought 6 and leaves with 7. So we're only going to count up to the red line. So that's half of the bond. So there's 1 here, and 6 is 7. So both of these have a +1 and a -1, not a huge difference. And then let's look at this one over here. The nitrogen on the end, well, let's cut them up. So brought 5 leaves with 7. That's -2. Ooh, that was kind of big. The guy in the middle brought 5 leaves with 4. So that's +1. And on the end, the oxygen brought 6 and leaves with 5. So that's +1. This one has the highest overall formal charges. You can't just add the positives and negatives together because they all add up to 0 because they have to. But if you want kind of a mathematical, objective way to do it, you could take the absolute value. So this is 2, 1, and 1. That would add up to 4. 1 and 1 is 2. 1 and 1 is 2. This has higher formal charges. That's not the most influential one. Now we need to choose between these two guys. This is where we use electronegativity. We want to put the negative charge on the electron. Let's just start that one over. We want to put the formal charge on the atom that has higher electronegativity. Is that going to be nitrogen or oxygen? Oxygen. So the negative formal charge is going to be more comfortable on oxygen because it's more electronegative. So if we look at the resonance hybrid of this one has more influence than the others do. If they all had equal influence, you kind of expect it to be more like this one where it's, symmetrical. But there's going to be a little more electron density over there. Any questions? Draw resonance structures and assign formal charges for organic compounds. So here we're going to have carbons and hydrogens, and then possibly a couple of other elements, nitrogen, oxygen, stuff like that. And this is for diazomethane, CH2N2. It tells us carbon is central. Okay, so let's start with the carbon. And what should we do next? I think the natural thing for students to do would be to hang everything off the carbon. It turns out that's wrong, but we'll just pretend I don't know that. That's a reasonable skeleton to start with. So we need number of valence electrons. We have 2 hydrogens, 2 times 1. We have 1 carbon, and we have 1 nitrogen. That's right, we have 2 nitrogens. Just checking to see if you're paying attention. It was going to be an odd number, and I knew that was not right. So we have 10 and 4 is 14 plus 2 is 16. I would encourage you to do that kind of math on a calculator. Okay, so we're going to start by counting the single bonds that we had to put in here. 2, 4, 6, 8, 10, 12, 14, 16. We don't have enough electrons, so we're supposed to make multiple bonds. Can we do that? No, because this nitrogen that's short electrons is bonded to carbon that has no lone pairs it can share. And this is the same way. If nitrogen shares its lone pairs, carbon will have more than 8, which is not okay, and nitrogen will still be short. So that tells me I did something wrong, right? So let's change the structure. Well, if the hydrogens aren't on the carbon, where else could they be? They could be on the nitrogen. Bless you. We can try it like that. I'll tell you that's not going to work. Either it's closer, but it's just not going to work. Or we could do it like this. So 2, 4, 6, 8, 10, 12, 14, 16 ran out of electrons. Now, carbon has lone pairs that it can share with the nitrogens that don't have enough. So we'll take that lone pair and share it with nitrogen. We'll take this lone pair and share it with the other nitrogen. And that's kind of wonky looking, so I'm going to straighten it out. Because we have to do resonance structures here. So this satisfies the octet rule. How else could we rearrange those multiple bonds? So you think of it as being, there's an extra bond here and an extra bond there, and this is being very egalitarian, and we're giving one to each side. But what if we showed favoritism and gave both extra bonds to one nitrogen? That would be a triple bond, right? So let's see what that would look like. Does that satisfy the octet rule? Yeah, it does. What's another thing we could do? We could put the triple bond with the other nitrogen. So I'm going to draw that guy down here. And then we can indicate that these are resonance structures by drawing the double-headed arrows. I want to show you something that speeds up assigning formal charges. So I'll do this in a different color. Let's look at carbon, nitrogen, oxygen, and fluorine. Carbon has 4 valence electrons. So I'm going to draw the Lewis structures just for the individual atoms, and I'm going to put one electron on each side, and then make another round and pair things up if I need to. So that's for 1, 2, 3, 4, 5. Oxygen has 6. 1, 2, 3, 4, 5, 6. And fluorine has 7. How many single electrons does carbon have? 4. Carbon almost always makes 4 bonds. These electrons are going to be shared with the other atoms. How many single electrons does the nitrogen have? It has 3, because this is a pair. So those guys are all happy with themselves. And there's 3 single electrons. Nitrogen likes to make 3 bonds. How many single electrons does oxygen have? 2. Oxygen likes to make 2 bonds. How about fluorine? 1. Fluorine likes to make 1 bond. So if carbon has 4 bonds, that's not what I meant to do. Carbon has 4 bonds, nitrogen has 3 bonds, oxygen has 2 bonds, fluorine has 1 bond. Their formal charges will be 0. So that's kind of a shortcut. So we have to assign formal charges. So let's look at that first one. We're cutting all the bonds in half. And before we count, does this nitrogen have 3 bonds? Yeah. Does the carbon have 4 bonds? Mm-hmm. Does this nitrogen have 3 bonds? I predict that their formal charges will be 0. So nitrogen brings 5, and how many does it leave with? 5. Carbon brings 4 and leaves with 4. Nitrogen brings 5 and leaves with 5. What do you know? So let's do this one. Again, cutting things in half. How many bonds does this nitrogen have? 2, not 3. That's going to have a formal charge. Here, carbon has 4 bonds. That one's going to be 0. Nitrogen, 4 bonds. That's going to have a formal charge. Let's see. Nitrogen brings 5, and this one's going to leave with 2, 4, 5, 6. So that one has a -1 formal charge. Carbon brings 4, leaves with 1, 2, 3, 4. This nitrogen brings 5, leaves with 1, 2, 3, 4. So if we don't follow this pattern, the number of bonds equal to the number of single electrons on the atom, then we're going to have formal charges. We can assign formal charges to this one by just comparing it to that one. This nitrogen is in the same situation that nitrogen is in, a triple bond and a single bond. We can do the math, but it's going to end up with the same formal charge. Here, the carbon, 4 bonds, just like there. This one, 2 lone pairs, 2 bonds, just like this guy. Formal charge is going to be -1. Any questions? So on the worksheet, you will be drawing Lewis structures for molecular compounds and polyatomic ions. You will be identifying which of them have resonance structures and how many. You don't have to draw them all, just the one. And then you're going to be assigning formal charges.